Okay, we'll allow time for people to roll in. Alice, you let me know when I can see the participant numbers ramping up there rapidly, which is great to see. Just let me know when we're good to go.
I think we'll give it a couple more minutes, and maybe once we reach either the 2-minute mark or 50 participants, we'll get started and go from there.
Very good. Allow time for all to join us. Always a challenge at the start of these webinars. So Alice, I think we might get going there. It seems to be slowing down the rate, and people can just join us as we go. Does that sound good? Presenters ready?
Perfect. Is everyone okay for me to record this?
Yep.
Yes.
So just letting everyone know this is being a recorded session. So look, thanks very much for joining us today. We've got a really interesting workshop at the back of a long and really detailed project, and very collaborative project between led by RMIT together with their colleagues at Monash University and AGL, and supported very much by AusNet Services, who have been there right through in helping inform this one. This workshop's been held on the lands of many traditional owners, depending on where you are. For me, it's the Wurundjeri people, and I wish to acknowledge them as traditional owners, and also pay my respects to their elders, past and present, and Aboriginal elders of other communities who may be here today. We joined to hear have some of the project participants share their insights. As I say, this project's been running a couple of years. It's been generously supported by C4net and AGL, who have contributed as well financially. So we're really keen to hear now how some of the challenges and some of the findings. So I'm going to hand over to Lasantha, who will take us through for the day for this workshop.
Thank you very much, James, and welcome everyone. Good afternoon. So welcome to our presentation on optimization of behind-the-meter DR generation assets with network constraints. So the main objective of this program is try to look at how to improve the demand response schemes for the commercial and industrial customers. So today's webinar is in fact lined up in this way. First of all, we will define what is demand response is, and then we will give you an overview of the project. And after that, we are going to present the key results and the outcomes of the 2 work packages in this project. One is on the machine learning-based energy demand prediction for demand response market. And the second work package we are going to present today is unlocking the potential of backup generators in demand response. And finally, we are going to talk about on the project recommendations coming out from the work package 1 and 2. So now over to you, Kedem.
Thank you, Lasantha, and thank you, James. And it's a great pleasure to be, I guess, here virtually, but to talk about this project that started more than 2.5 years ago, I think, late 2020 in terms of the application. And we are talking about demand response. And the demand response in a nutshell, it's an opportunity for energy users to take part and provide grid services. This is really a representative of what is a circular economy. An opportunity for customer energy users to help with the transition to renewables. And the way they do it is that they can reduce demand when requested by participants in the market. The timing for usually those requests will be when the demand surges. And so by reducing customers' demand, they reduce the pressure on the grid. And that helps that balance between supply and demand. And that means that reduces costs, because you don't need to supply those high peaks, which are usually more expensive, much more expensive than others. So just to give an example, we're moving from, let's say, $100 or $200 per megawatt to $15,000 per megawatt hour in the wholesale market. So that's those are times that it can help reduce costs, but also we increase the reliability. And as part of AGL sees it as part of its strategy to foster, to accelerate the transition, and one of the ways of doing that is through behind-the-meter assets. In this regard, my role is I'm the Commercial Industrial Demand Response Manager, and it's my mandate to help energy users, business energy users, develop these capabilities and then leverage them in the market and use it. As I said, the circular economy point comes here quite a bit because energy users can become energy grid services providers. So it's a very important area in the market's very well acknowledged. But of course, one of the aims was to see, well, how can we address challenges that currently exist and therefore unlock more of the potential, more of the value to both energy users and participants that work as aggregators. This is how we got to, we're happy there was an opportunity in 2020 by C4Net to provide grants for research. And HL is a key believer that in this collaboration between the industry and universities, academia, try and work together to identify solutions to problems that exist with challenges that those solutions can accelerate or can overcome. Specifically today, we talk about two key elements. One of them is around baselines. And the question there was, can we find a smarter or better way of measuring performance? And in this project, we'll be talking about the idea was machine learning. Can we use machine learning to provide better baselines, which are would be a better way of measuring and verifying outcomes? Because the challenge is that with demand response, you are making a change and you don't know what would have been if you didn't take action. So the customer does something, the end user does something, you change the situation. So it's about forecasting and trying to assess what would have been, so you can measure that versus what actually happened. The other part of the key part of the project was around the option for backup generators to export into the grid. So most energy users that have backup generation, it's always oversized, or it's not oversized in a negative way. It's sized in a way that it can provide backup to whatever load is on site. That means that there's always spare capacity. And there always the question is, can that spare capacity then be provided, can be exported into the grid? Now, it's not a simple point from a technical perspective, because the networks do need to manage the grid. They need to make sure that security is always within the desired levels. And now some energy users have gone through the process and can export, but it's a process. And one of the things we're trying to do is say, can we identify what are the challenges of that process and what could be done to facilitate it, make it easier. So it means that end users either know, it's easier for them to know what the process is, and maybe there are additional solutions that can adopt and they know what to do and what can be adopted in order to enhance the success of these kind of processes to enable the generator to export. As a nutshell, that may mean that a given energy user who wants to participate in demand response may then be able to double their capacity and increase the consistency of what they can deliver, because then it becomes less about what is the load on site, and which can change from daytime to nighttime and so on, or from the morning to afternoon, and becomes more of the generator's capacity to generate energy delivered into the grid. So those are the key points that we'll be talking about today. The third point was around batteries, what tariffs could incentivize the uptake of batteries, and which is, of course, another critical part of the transition, which is a very big, and it comes across all energy users. I'd like to pass on to Mahdi, who's going to take us into the finer details of the project.
Thanks, Kedem. So I'm Mahdi Jalili from RMIT team. Pleasure to be here today. I'm going to talk a little bit about the first work package that we had in this project, which is about machine learning and the opportunities that machine learning brings to do more analytics on demand response and how we can do a better baseline setup in demand response programs. So when we started doing this research, we tried to see what kind of opportunities data analytics and machine learning can bring for more efficient demand response. And what we found was that the baselines that we use in demand response is the way that we can apply machine learning techniques to do more and more targeted, more efficient and targeted baselines. So you may know that when you're participating in demand response, you always need to have a baseline to compare your consumption, and then it obtains the monetary benefit to the users. So this is the way that it works. This is the current market setup. So for example, let's say that tomorrow we're going to have a demand response event. So your consumption is calculated for the past 10 days. And then that is the baseline consumption for tomorrow's, your baseline consumption for tomorrow, for which we don't know, but that is going to be the consumption that we're going to use as a baseline. Then you participate in the program, your actual consumption is calculated. The difference between the actual consumption and the baseline, which of course the actual consumption should be less than the baseline. That is the reduction that you are providing by participating in the program. That reduction is your contribution to the demand response program. That is what will be given you as monetary benefits. But this is what the market is currently using. Here we just try to see whether we can improve this baseline by simple and explainable data analytics and machine learning models, by considering some auxiliary data like temperature and that kind of things. So the goal here was to use machine learning techniques and build easily understandable and interpretable models. So this was the key thing. We didn't want to use very sophisticated deep learning or black box models. We knew that by that kind of models, we could do better prediction, but we wanted to use just simple models so that we can explain it to the broader industry that by this simple model, this is going to be the forecasted demand, and this is going to be the baseline that you'll be using for the market. So we used two simple models here, and then fed the historic energy demand data recorded by smart meters, and some factors like temperature, that kind of things were also used in our prediction models. So these are the simple models that we used. The first model was a linear regression model, very easy model. Just X is our input, Y hat is our output. That is the predicted output, which is going to be the demand. Let's say demand for tomorrow, which is the target date for demand response. The other model is again a very simple regression, but this time it is a bit more sophisticated than the first model. But still, it's really easy to explain and to interpret the relationship between the parameters. So these are the two models that we applied on the data. So this is the way that we do our prediction. So it is very similar to any prediction and regression task. So we had the data from a number of commercial industrial customers there. So we had the real demand response data, their consumption 10 days, 20 days before the demand response event, their participation in demand response event, their actual consumption as being participated in the event. We used it for our training. So we divided the data into training and testing. Training data was used to train the model, get the unknown parameters, and then we tested on parts of the data which was unknown for training the model. These are the snapshot of the customers that we used. We had more customers, but here, just for the sake of simplicity, we have given the data for some of these customers. So I have 6 customers here. So we had 2 data sets. One data set was a number of customers for which we had the demand response information. The other data set we used it for just checking as a kind of proof of concept for our models. But for that data set, we didn't have the demand response information. We just had the consumption information, but a finer resolution consumption information for that customer. So we had the chemical plant, telecom, 2 telecom operators, a university, and 2 water utilities in this data set. Almost for, you see the dates for these data sets, something like 2-3 months. It varies depending on the data set. And we had the consumption profiles of each for 48 consumption values for a day. So every 1 consumption per 30 minutes. And the second data set, as I said, was more data we had from this customer. This is a water utility, a large water utility, and we had more information about the customer, some auxiliary data, but we didn't have participation of this customer in the demand response program. We just applied our prediction models on this customer. And this is the outcome on the first data. You saw that the models were pretty simple models. So here, what we see is just the baseline, just the prediction of the model, and the baselines compared with 2 simple models that we used. This is the accuracy. The higher the error, so that is root mean square error, that's an indication of error. The higher the error, the lower the accuracy. You see that the baseline is not capable of producing highly accurate, except for university, which is pretty accurate. Indeed, what we got was that usually for other data sets, the AI models were more accurate, but for university, for some reasons, the baseline model is even more accurate than the AI model that we use, possibly because of less data that we had from that or for any other reason, but we didn't have more data to explore. But what we found was that usually for almost all other customers, we can get better results in terms of the accuracy of the model. And when we consider temperature corrected data is even more accurate. And this is the actual consumption. You see that the blue line is the actual consumption. And you see that they have participated in that demand response event, which has lasted for 5 years. So they have reduced their consumption. So the market, the current the market is that it is compared with the baseline, which is the red line. But the AI model predicts the actual baseline, I would say, which is the green line. And we are suggesting that it needs to be corrected. It needs to be compared with the actual baseline, not the baseline for the past 10 days. And we also did a little bit of work on the monetary benefits. So what is the implication for the monetary benefit of these customers? I would say that this is not AGL's position or any other demand response aggregator. This is what market is offering to these customers, and AGL and all other aggregators, they have just very minimal role in that, but this is largely the market offer, demand response market offer to these customers. So this is comparison between the AI-based, the machine learning-based baselines and the current baseline. When it is positive, it means that they are underpaid. When it is negative, it means that they are overpaid. So interestingly, one customer, university, we saw that we are not predicting, we are not getting good performance for that customer. That particular customer has been overpaid, not overpaid, but the baseline, the current baseline is in favor of that customer. While for the other customers, for example, for a telecom customer in Victoria, if the market uses the AI-based baseline, which is better, more accurate baseline, the customer is likely to be paid around 90% more if they participate in the demand response program. We also applied, as I said, the data on the second customer, which is a large water utility, but we didn't have the ground truth data on the participation of these customer in demand response program. So we didn't know whether the customer participated in the program. We just wanted to see how our models are performing in the customer. So we considered a little bit more complexity in our models, and we applied time window, which is a pretty classical model in prediction tasks, and we just wanted to see how it's going to be the performance. And this is just the outcome of our prediction. And you see that when we have in the right, when we have that time window, we always improve the baseline. And by considering given temperature, we can do even a bit better job, and the baseline will be improved, but not necessarily for all cases. So water utility consumption might not be that much dependent on temperature. That's why we are not getting that much improvement with temperature, but almost across the board, our simple AI models improve the prediction accuracy. So just as a summary, what we found was that the current offering in terms of the baseline can be improved by some simple AI-based models. They are not difficult to explain. They are pretty easy to interpret and explain to industry, and they can really understand what is the relationship between all these parameters. But the outcome might be more beneficial to the market. It might encourage more customers to put their reserves on the market and to participate in the market. I think that's it for me. Back to you, Lasantha.
Okay, thank you very much, Mahdi, for the work package 1 outcomes and the results. So the work package 2 was in fact mainly focused on the commercial and industrial customers' backup generators. And we saw there is a huge potential of using these backup generators in the demand response program. But the key question was how to unlock this potential. So with that in mind, we have set out few objectives for this work package. The first fact was what are the contributing factors for the backup generator export limits? So that is one of the major constraints faced by C&I customers. So we have to do more systematic study to understand what are the factors really affecting the exports. And also we looked at what could be done to improve these export limits. So therefore we have looked at various strategies as well, how to improve the export limits from backup generators. And in addition to that, from the review perspective, we have carried out 2 tasks. One is we have looked at the best ways to synchronize the backup generators, and also looked at what sort of regulatory and the DNSP requirements are there in place for these backup generators or any generator which is set to export to the network. And finally, we look at how to use the biodiesel and what sort of feasibility exists to use biodiesel for these backup generators so that it can reduce the carbon footprint. So let me get started with the first part of our analysis. So the first part was mainly focused on the barrier analysis, because we saw some of the CIN customers had a good potential to use their backup generators in demand response, but somehow it was limited in various different ways. So therefore, what we did was we did a very comprehensive barrier analysis. So we have segment down the barrier analysis into 3 types. One is the location-based barriers, because if we take a distribution feeder, the backup generator can be located any part of the network. So therefore, based on the connection point of the backup generator, there could be some barriers. So with that in mind, we have done a series of studies. And the second barrier analysis was done looking at different network models, because the network models could vary from urban, rural, semi-urban, and CBD. But the fact is, most commercial and industrial customers doesn't exist. The examples that we took over didn't exist in the CBD. So therefore, we have to find out the network models which replicate the behavior of urban, semi-urban, and the rural commercial and industrial customer setting. Within that in mind, we have done a series of studies to characterize the impact of connecting a backup generator to the network. And the final aspect was the time-based barriers, because at some part of some time of the day, there could be some constraints, and some time of the day, there are no constraints. So therefore, we thought we better do a time series study as well. So in that in mind, we have done quite a number of quasi-dynamic simulation to see how these network barriers going to change over the one day. And in terms of the technical side, we have looked at the voltage limits as one of the technical aspects which limits the exports, and thermal limits, and finally the short circuit limits. So here in this presentation, I'm mostly going to talk about the voltage limits. And we found that some cases the thermal limits can also play a part. But in our analysis, we haven't seen any issue coming from the short circuit limits for the backup generators which are existing in semi-urban, urban, and the rural settings, because those networks can handle the short circuit capacities according to our studies. But we know that there could be some issues coming into play when the network is a CBD-based underground network. So what we did was to carry out this one, we have looked at what sort of networks there exist to simulate these scenarios. So we saw that CSIRO has a comprehensive list of networks, 20 plus networks, but we can't really select all 20 and do this study. So what we have carefully did was we have looked at their characteristics, and we have shortlisted 4 network types from the taxonomy study. One was the urban New South Wales, 2 networks coming from the urban New South Wales. And you can see, even though these 2 networks represent similar urban settings, the capacities and the number of bus bars and the lines are different. And also we looked at the urban Victoria network given in the taxonomy study. It's a pretty much big network compared to the New South Wales ones. And also we have looked at the short rural Victorian network as well. So using these 4 representative networks, we have carried out the barrier analysis. So let's look at what we have come up with, the impact on the backup generators connected to different locations in the network. So here you can see 4 voltage plots. And in the top corner, you can see the urban New South Wales. And we have looked at what would happen to the voltage when you connect the backup generator at the beginning of the feeder, middle part of the feeder, or end of the feeder. So we have clearly seen in some cases, when you connect the end of the feeder, it would actually help the voltage of the network. And in some cases, as you could see, the voltages could go even very high values, but still they were within the limits. But clearly this analysis shows the location has some impact as well, where we connect in the network. So from the network perspective, sometimes it's better to keep the flat voltage profile. So connecting at the end of the feeder sometimes helps the network operators to improve the voltage profile. And at connecting at the start of the feeder, still it does not really mitigate the voltage drop issue in the feeder, but sometimes it could give rise to some capacity issues as well. So that was the one outcome we have seen. And then we have looked at what would happen if we increase the loading level on the network. So that means we have looked at what would be the capacity of the generator as a percentage of the total load of the network. So what we did was we incrementally increased the backup generator capacity and look at how the voltage is going to increase. So we have clearly seen, obviously, there are voltage increase issues in the network when you increase the size of the backup generator. So the size of the backup generator is playing a major part in this export limitation. So these are just some representative results. We got a lot of other results as well. But with this in mind, we have looked at what we can do, in fact, to improve the export limit. So at this point, most of the cases, there is a one single number for each CNI customers to import the active power. For example, if we consider a CNI customer connected to a New South Wales network, for example, there could be a limit of 2 megawatts. And 2 megawatt limit is defined for the ultimate worst case. But if you do a complete time series analysis, we could see that that limit can be increased to 4 megawatt in this particular case. So likewise, we saw that export limit is not a one single number. It could be a number which could vary from network to network. Obviously, that will be captured usually in the connection studies. But when it comes to the time of the day, it plays a major role. For example, in this particular case, 2 megawatt can be increased to 4 megawatts. So that means you can double the export limit if you change the static export limit to a dynamic export limit. So we saw there is a huge potential to implement dynamic export limits for the CNI customers or the backup generators, so that it can increase the export capacity. And in addition to that, we have looked at how the backup generator should be controlled. So there are two methods of controls we can apply for the backup generators. One is called the PQ control, which means active and reactive power control. So in active and reactive power control, we precisely control the active power output or the real power output of the generator. And also we keep the Q or the reactive power at a constant value at 0. And the other option is PV control. PV control in the sense change of control of the active and the voltage of the terminal. So in this particular control strategy, the backup generator maintains a constant active power output while maintaining its terminal voltage constant. So we looked at how these two strategies going to play for applies to a backup generator. So in the top graphs, you can see when the PQ control is applied, that means active power or the useful power is kept constant from a backup generator, and also the reactive power gets constant. You can see under certain situations, the voltage can go up, which is shown in the green color plot. But it keeps both P and Q constant. But if you apply PV control, which maintains the active power constant as well as the terminal voltage constant, you can see the voltage can be maintained constant throughout the day. So that is one advantage, so that the voltage do not change with the time if you apply the PV control, so that in such situations, you can improve the export capacity and also mitigate the network constraints. So, but we have seen one thing, that means we can't really always apply PV control or PQ control. There should be some operating flexibility for the backup generators to operate. So if they have operating flexibility, then it can also bring the benefit to the CNI customers, and also it can provide more benefits to the network as well, while mitigating the network bottlenecks. So those are the main outcomes we have seen, results we have seen from our simulation studies. And in addition to that, we haven't included it here. We have carried out a detailed technical review of the DNSP connection standard with regard to the backup generators. And we have reviewed the local, national, as well as the international standards as well. And in addition to that, we have looked at the feasibility of using backup generator, feasibility of using biodiesel for the backup generators in this study. Okay, let's look at what are our recommendations here from this project, mainly from the work package 1 and work package 2. So the first work package, we have looked at how to use the machine learning techniques for the baseline calculations. So machine learning techniques can be applied to weather-dependent loads. That is what we saw. That means if a certain load, for example, a shopping mall, has a strong correlation with the temperature, then obviously we can apply the machine learning techniques to improve the baseline calculation. And we saw that advantages as well from the Mahdi's presentation. So we have seen it very consistently throughout our study, the first work package. So we believe it's better to use the machine learning techniques, more specifically interpretable machine learning techniques for the baseline calculation for the weather-dependent loads. And also another recommendation was the dynamic export limits for backup generators. As I have shown earlier in the plot, by using the dynamic export limits, we can maximize the benefit both to the network as well as the CNI customer as well. So rather than defining the static limits, it is better have a dynamic export limit for the backup generators. So that is one of the recommendations we came up with. And I think it is very consistent with what is happening in the low voltage networks as well, because here we have looked at the medium voltage networks. That is, I forgot to mention. So it is very consistent recommendation with regard to the MV networks here. And also we saw some advantage of using flexible operating modes for the backup generators, because if you fix the operating mode, the network benefits it can deliver will get limited to that particular mode. But if you use flexible operating mode and operate the backup generator, it can maximize the benefit, network benefits, as well as it can maximize the export capacity as well. So therefore, one thing we could do is we can assess the backup generator operating modes when you're doing the connection study. So that could be one recommendation we came up with. And in addition to that, coming out from our rigorous review, we saw that different DNSPs use different connection standards, synchronization standards, as well as intertripping standards. And we believe in it better that we have a consistency across all these standards so that the CNI customers would be more encouraged to use their backup generators in the demand response program. So that is one thing we saw. And finally, the biodiesel for the backup generators. So we have analyzed the complete supply chain and also the technical feasibility of using the backup generators in the demand response programs. Biodiesel for the backup generators. So we saw the supply chain exist, but the fact is that should be further supported by the state or the federal governments so that CNI customers can get the appropriate technology as well as the biodiesel products to use in their backup generators so that it can reduce the total carbon footprint. So these are the main recommendations we came up from these two work packages so far. And we have another work package 3, which is looking at the network tariffs. And we believe we are planning to take, it has some further benefits to discuss in the future. So at this stage, we would like to take any questions you have with regard to our project.
So Lasantha, thanks very much, Lasantha, Kedem, and Mahdi for that presentation. There's a couple of questions that have been popped in the Q&A, and I encourage the audience to use the Q&A function to just post their questions. Lasantha, can you see those?
Oh, yes.
James, one of them is about, the first one is about machine learning. Maybe I can comment on
Please.
that.
Yes, yes.
Yeah. Yeah, the question is whether we use just 10 days for machine learning approach, past 10 days or more. For most cases, we didn't have that much data, but to make it comparable with the baseline, we used 10-day for our machine learning approaches. But of course, if you use more data, you can do even more accurate analysis. But our aim was not doing more accurate prediction or the most accurate prediction. If you wanted to do that, you can easily use black box models or deep learning models. The aim was just to see how really simple models perform when applied on these kind of data. But we used it only for the past 10 days.
Thanks, Mahdi, and thanks, Bani, for the question. Who'd like to tackle Peter's question there around did the backup generators incorporate a voltage droop or other reactive compensation to mitigate the voltage rise?
Yes, we use the voltage droop type control here, but it is slightly different because we try to have an integral function as well to correct the voltage back to its nominal value. But we haven't looked at the other reactive power compensation strategies in this project because it's out of scope, because our main sole focus was how to optimally utilize the backup generators in the demand response program. So we looked at the strategies that we can implement around the backup generators only. We haven't looked at the StatComs or the capacitor banks or any other inverter-based strategies here. It's just focused on the CNI customer backup generator and its functionality, what it can offer to the network.
Yeah, thanks. And that was very much
Yes.
in the project design and everything of how we approach this in really looking at how the aggregator or the retailer could work with and understand better the network needs such that they could actually better assist their customers and understand that connection approach or the data requirements. Just before we do peers, maybe just sticking with Daniel here, just because it's still Mahdi on the on the machine learning modeling here. Do you filter the 10 days by factors such as weather and day type, for example?
We do not filter, but we do consider temperature and weather condition. So weather condition is mainly temperature that we are considering as a covariate in our prediction models. Yes, we do consider temperature as an input to the model. So we had two different cases with temperature and without temperature. And usually temperature gives us better accuracy.
And what about CNI customers being or CNI sites, being that they may not have a ubiquitous operating profile every day. Some of them may have weekend closures or shift impacts there. How is that taken into account? Yeah,
that is being considered already in that 10 days. Possibly Kedem can explain it a bit more, but it is considered. So that is, we know that the load is significantly different with weekdays and weekends for these customers, and that is already being considered in that 10-day. The original 10-day that is being used by the market.
Yeah. Just to confirm and clarify, weekends are excluded from the baseline, including public holidays and also previous events. So if you take a 10-day average, if you had an event previously on 5 days ago, that they would be excluded, and you have the option to go back up to 45 days to find a different day.
Okay, I assume that's what Daniel meant with that question. Daniel, if that's not what you meant by day type, please jump in and let us know in the chat there. There's a question on the biodiesel, Lasantha, from Pierre. Has there been any research into identifying the potential types of biodiesel to be used by the backup generators? I'm referring to the best option striking a balance between cost effectiveness and least emissions footprint.
In fact, in our study, we have identified different biodiesel blends, but honestly, we haven't looked at the cost effectiveness of different blend or not. So it is a little bit out of scope at that point, because there are so many different types of blends. But we saw as a whole whether the biodiesel supply chain exists, or what sort of technology we need to have for the backup generators, or is there any specific biodiesel generator models exist? So those are the things we looked at. And we saw there is a big potential, but probably cost effectiveness of a certain blend would be an extra study. I think it's a good point. Probably worth further analysis. Maybe Kedem can also put some.
Yeah. So I could say that we are aware of different types of kind of grades, the 5%, 20%, 100%. And I guess, as Lasantha was saying, that's kind of a separate question or in parallel to the supply chain. So first of all, the availability of biodiesel. So, and the availability is important. If someone says, I want to use biodiesel as, to reduce emissions, first of all, that option exists. Then the question of what do you use? Do you use 20%? Do you use 100%? It comes also into kind of commercial discussion, debate about how much do you need, and 100% is more expensive, has some challenges with it. But we didn't go into that level of details. It was more around identifying whether it is possible, rather than trying to pinpoint the best solution, which is a bit of an open question for whoever would want to use it, rather than, a definite answer.
So the next question goes a bit to the heart of the initial conundrum that sat there with the project, and that was of retailers having to work across, they serve their customers, but be across multiple DNSPs, and this question of to what degree could things be standardized or have consistent approaches, or how bespoke is it to either a DNSP or an area within DNSPs, because that's something that's been really hard for retailers to deal with, is to how to advise their customers, given that it is they get quite bespoke solutions back each time, or approaches, and trying to work out, is that inherent because of the technical differences, or is it more that there is an opportunity to do some optimization and some harmonization there? Kedem, I wonder, feel free to answer the question directly or more broadly, in that, some of your observations of what you've learned from in going through this project, and the differences that are there from the network perspective.
Yeah, so there are differences, and I think the question gives a good context to that, of each network manages in the way it sees fit, and that follows their strategy. The differences sometimes come on thresholds between saying, the 1 megawatt could be a threshold for that requires intra-chipping with one DNSP, and others say 1.5. And what we've been trying to do through the research, and I'll kind of defer it more to Lasantha in terms of the outcomes, is to explore that option of trying to raise a discussion whether you can get standardization, which then for some customers that have, let's say, multi-sites, of course, different DNSPs, there could be a bit of an easier process to identify which sites could go through the process and are likely to go through a lower cost process, or would fit into one category, which require less, like a shorter process. So it's a wide area there, but the intra-chipping threshold is probably one of them. The technology that is used for intra-chipping can make a big difference because of the cost, whether it's fiber optics or RF signals. But I'm here more as, raising the question. I'll defer to Lasantha in terms of talking more about the recommendations.
Okay, I think this is a really good point, in fact, because what we see from our study is each network behave different manner, because we have used 4 representative networks. All 4 networks have its own characteristics. But the standards can be built on the fundamental principles. And we strongly believe, in fact, we have reviewed thoroughly all the DNSP standards. They're all built on same fundamental rules. There's nothing different. So, but what we see is the evolution should happen on these standards, because the new things are coming in. One is the dynamic export limit. So the old days we use the static one single export limit. So why not we use the static, the dynamic export limit? Because we have now good monitoring tools. In the low voltage grid, we have the smart meters. So obviously we can implement the dynamic export limit. So that could be part of the standards which can bring up in the future. So likewise, we can also propose the different operating modes. Even it will apply for the inverter-based resources as well. Why not we try different operating modes? So likewise, we can build and evolve the standards into the next stage with these new techniques. That is what we can do. But at this point, what we see is they're all based on the same fundamental principles. So we can't really apply one figure for each network. So it's because each network is different from another. Because their characteristics, their length, number of loads, number of customers, and there are so many other factors, in fact, dictating that export limit. But as long as you follow those fundamental principles and assess the export limits, that is what we should do. But the number of requirements and the things should be evolved. That is what I feel should happen.
Kedem, I might, I'll go to this other question here that's been raised in the Q&A, but might get you to, when we come back to you afterwards, just sort of on notice of, from a retailer or aggregator perspective, what would that be worth to you? I'm not, you know, in terms of that harmonization, in terms of how much of a barrier it is to utilizing demand response now or engaging demand response. Okay, so I'll come to you in a moment for that. One, the question that's been posed in the chat is around, very much one around the minimum demand type challenges that we've had there. Did you look at the increasing the demand as a demand response event?
Yeah, that's a perfect question that leads to a whole different way of activity. But the minimum demand is, of course, one of the things that we're looking at now, because that comes in conjunction with a reliability element or security for what happens when demand goes very low and the grid supported, but also from a carbon emissions perspective. So with the increasing adaptation of solar, both behind the meter and in front of the meter, we're seeing more and more negative prices on the wholesale market during that peak solar time between 10 a.m. to 2 p.m. So we're definitely looking at options where demand can be shifted. I wouldn't use the word increase, like it'll be specifically increased during that time, but it's more about shifting demand away from high demand or classically high demand periods and high prices to times where there's a high penetration of renewables, and usually that comes with low prices in the market. So that's definitely something we're working on. Hopefully, I mean, if anyone has interest, more than happy to afterwards have a more detailed conversation, but we're definitely having one trial with a customer already, a very large customer of ours. And it's something that we plan to expand, but it's still in a way early days to see how can you make it happen and what types of energy uses can do it. Would never be looking just to increase demand for the sake of it, because that doesn't have an inherent business value. But that's what we're saying, not increase, but shift demand from different times to better align with the renewable profile.
Very good. And with respect to that, in terms of that barrier to signing up new customers, adopting them and bringing them into demand response schemes, just that level of bespokeness that sits there at the moment, and how big a challenge that is for you?
Yeah, great question. It's still most of the work we do are now very large customers, and that usually tends to be bespoke. That means that when we talk about baselines, we may actually have specific baselines to fit the customer profile. If it's a bilateral agreement, it's some agreements that are dependent on the market, and the baseline is what is indicated. We can't change that. But we are looking at ways to simplify demand response so that things become less bespoke and more standard thing. And that very much aligns with how we contract for energy. The big customers may have specific requests, but as you go down in the volume contracted, then agreements become more standard, more simple, because the size of customers may not have special requests, or they may not really be willing to address it, or means we need to simplify things. So I think that's part of the process that we and others are looking at to make it easier to do. And it's a journey, because some customers may not have the attention to deal with it. It's not an easy look. You still need to do some change of process on sites in order to participate. It's a physical activity rather than just signing a contract.
Yeah, it's one of those really, really big challenges of that transition, that it's not just all virtual, it is matching up that physical infrastructure and the challenges of trying to work within networks. And of course, the networks are becoming far more dynamic in how they can manage their networks and everything as well, and the technology developments they're doing there, which are really quite amazing. I would like with that to thank all of our presenters and researchers today for their participation. Also, very much from the audience, we've appreciated the questions coming in. So thank you very much, and for the guys addressing them. If you do have any feedback for us, please let us know at info@c4net.com.au. We'd love to hear of ideas and thoughts following the webinars. We will post the recording with the project on our project page. If you do have further questions, please direct them through either to C4Net or directly to the researchers involved. So with that, sorry, Kedem.
Well, there was another last question about
just one.
Pierre.
Oh yes, one more from Pierre. Would you like to address that?
Yeah, I can say that the aim of the research was really around trying to identify solutions that, let's call it objective. This is for anyone who takes part in demand response. It was less about the commercial aspects of aggregation and value per customer. It's not about whether it's worthwhile for customer to participate. It's more around, can we use machine learning to improve the way we measure the baseline activity, and also about the exporting, which is again about how can we increase the utilization of assets. So how can we facilitate and simplify the process to be able to do that? So it's not about a retailer or aggregator or DNSP, it's more about the basics of demand response.
Thank you, and thanks, Pierre. Okay, thanks so much for joining us today. We look forward to hopefully having you join us for more webinars in the future. Okay, thanks guys.
Thanks everyone.
Thank you.
Bye everyone.